So the topic of this video is the calculus of the polar coordinate system. So we're going to be starting off with finding the area of a region defined by a polar coordinate graph. So we just got done, hopefully you've been practicing graphing your polar coordinates equations, and so which is going to be of course very important, because whenever, if you remember from Calc 2, we would find, you'd have to graph the, draw a graph first and figure out the region that we're talking about, and then find the area of that region. So I'm thinking, especially if you remember from Calculus 2, when we're finding the area between two graphs, and even when we're spinning, find the volume, we'd find the region first, the regions that's enclosed by the graphs. So that same kind of process here, but we're dealing with polar coordinates instead of rectangular coordinates. So it's also a little bit strange because we're dealing with different variables. We're not dealing with x and y. We're dealing with r and theta. So generally, in a polar coordinate system, the equation is r equals something involving theta. So the r is the dependent variable and theta is the independent variable. Just like normally we think of as x as the independent variable and y as the dependent variable. So that also produces a unique challenge, because if you remember also, when if you're using integration to find area, the process is dividing the area that we're trying to find up into little pieces. Now in rectangular, because it's rectangular, we divide the area up into rectangular slices. But because a polar coordinate system is based more on a circular system, because we're going out a certain distance and then turning around the outside of the circle. So instead of using rectangles, we're going to use sectors. So you can see right here that if I'm trying to find let me grab a different color. If I'm trying to find the area of this region in here, okay? So I'm going to divide it up just like I normally do, divide it up into little pieces and then add up all those pieces. That's what integration does, right? So you can see here's an example of one. So what we're doing is breaking it into a bunch of small angles. So here's one sector right there. So if I'm finding the area of this sector plus the area of this sector, so we're thinking of this little sector as a part of some big circle. So we're thinking of it as something like that. Then here's another sector here. I should be using different colors here, I guess. This green one represents a different sector. And what is it? Red represents this sector here. So all of those, again, all those sectors are going to add up to the total area. And when theta is bigger than 0, then it's going to be approximation. But we're just like if you remember in Calc 2, when we let the thickness of the rectangles approach 0, then we'd have an infinite number of these teeny little rectangles. So we're going to do the same idea here. We're going to let the angle of that kind of defines the sector to approach 0, which means there's going to be an infinite number of these little sectors in here, and then it'll be the exact area. And so you can see all that was to explain that this is the formula that you're going to use when you're finding area in a polar coordinate system, because the area of this sector right here, because again that's what we're doing, is some little piece of a circle, you're going to take pi r squared, that would be the whole circle, and we're going to multiply it by some theta, and that's where the d theta comes in, over 2 pi, because this is what fraction of the total circle. This is the total circle. This is what fraction of the total circle it is. And so notice that the pi's cancel out, and that's where so you're left with 1/2 r squared d theta. And that's this formula right down here. And the limits of integration are in terms of theta, because we're integrating from a certain angle to a different angle, right? So that's the idea. So you want to keep this little box here in mind. That's why I boxed it for you. That's going to be the form of all of your areas that you're finding. So the first step, of course, is to get an idea of what this thing looks like. So in this first example, it says find the area enclosed by the following graph. So r equals cosine 2 theta. Now, of course, you can throw that in your calculator to get a picture of what it looks like. But you also need to be able to do these things by hand so that you know where the different breaks in the graph are. So, for example, in this case, I'm going to start off, and it might be helpful when you first begin to start doing some little r and thetas here. So if I plug in 0 for theta, then I know in this case cosine of 0 is 1. That means r is 1. When I plug in, let's do something that's something that we know, like say pi over 6. So when I put in pi over 6 in there, I get, of course, when I put pi over 6 there, it's 2 times pi over 6, so I'd have pi over 3. So we're thinking, what's the cosine of pi over 3? Well, the cosine of pi over 3 is 1/2. And then if we do, say, pi over 3, 2 times pi over 3 would be 2 pi over 3, and in that case, cosine is negative 1/2. So let's start trying to get a picture of this. So when I plug in 0, I get 1, and let's just make this, because this is really teeny. Wow. So I'm going to say that each one of these, or it takes, let's go out to say 1, 2, 3 of them is 1, just so we have, well, let's make 5 of them 1, just so you can see a little easier. 1, 2, 3, 4, 5. So that's 1. That's 2, just so it's a little bit more blown up. So when I plug in 0, I get 1, so I'm right there. When I plug in pi over 6, which we know is along this line here, right? That's the angle I'm facing. So I'm facing pi over 6. I get out 1/2. So I'm going to go out this thing. So that would be out 1, 2, 1/2. So I'm right there. Okay? And then this says when I get to pi over 3, which would be way up here, right? That's pi over 3. I'm actually negative 1/2. So I'm going out the back side. So that would be down this way. 1, 2.5. That'd be out there somewhere. Now I know between here and here that it's shrinking. It's going from 1 down to 1/2. So that means, and it's following a circular pattern. So basically this thing's going to go something like that. And the question is when does this thing hit 0? And that's a very good question, because it has to hit 0 because it becomes negative, right? So let's back up a second here and say, I wonder what happens. Let's put a little negative 1/2 down here and pi over 3. I wonder what happens at pi over 4. When I plug pi over 4 in there, 2 times pi over 4 is pi over 2. Cosine of pi over 2 is 0. Aha! So at pi over 4, which would be right here on this guy, I'm going out 0. So by the time I turn facing this direction, it's gone down to 0. Now, because cosine is symmetrical and it follows, it repeats itself a lot, we know that this thing is actually going to, in fact, if we remember our trigonometry, we know that this thing means that the period is equal to 2 pi divided by 2, right? So that would be pi. So we know this thing is going to start repeating itself after pi. So by the time I get to pi, it just repeats itself. So we've done 0, pi over 6, pi over 4, pi over 3. So let's throw in a pi over 2 here. Pi over 2, would, if I plug it in there, that's the same thing as pi. Cosine of pi is -1. So that would be -1. So this thing's going to go to -1/2. By the time it's facing straight up and down, the pi over 2, it's at -1. So it's going to go out 1, 2, 3, 4, 5, and be out there. So we know this thing's going to go something like that. And if we keep going, let's go to the next one. How about, let's see, pi over, or let's do 2 pi over 3. So when I do 2 pi over 3, that is, I will plug it in there, that's the same thing as 4 pi over 3, which would be cosine of 4 pi over 3 would be -1/2. So now I'm facing, 2 pi over 3 would be facing up in this direction, right? So I'm going out -1/2 in that direction. So that would be right about there. And, okay, so since we've already gone through this graphing before, hopefully you're kind of getting the idea. So what happens here is we end up, this thing comes down like this. And so it keeps going, and when you get over here, oh, and once you get back to, this is at pi, or no, this is at 3 pi over 4. That's when it hits 0 again, right? At 3 pi over 4. If I put that in there, that's going to be 3 pi over 2, which cosine is 0. So when it hits here, we're at 3 pi over 4. Okay, so the point is, and if you graph this on your graphing calculator, you already know what it looks like. It looks something like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And it finally ends over there. So that's what it looks like. And if we're trying to find the area enclosed by this whole thing, that means we're actually looking for all of these little leaves or petals, if you will. Okay, but it doesn't really make sense to calculate all of them, because we know that one petal, all the petals are going to be the same, and so it really makes more sense to, if we want to make this as simple as ourselves as possible, what I would recommend doing is just focusing in on just this little half petal here, because it's easy to tell which theta and which which theta and which r make that. And so if we just focus on, if we can find the area of this little half petal, then all we have to do is multiply it by 8 to get all the petals, because we know there's a symmetry here and these are all the same size petals. So let's focus on that. So this thing begins at 0. So if I'm going to write the integral, I'm going to say the integral from 0, and we're talking radians, of course. We're going to go from 0 to, and remember we hit this spot right here at pi over 4. So I'm going to put a little pi over 4 up here. And the formula is 1/2 r squared. So we need something squared, and this is d theta out here. And since it's, but remember I'm doing 8 of these. There's 8 of these little half petals, so I'm going to multiply 8 by the 1/2. So that leaves a 4 out front. And then all I have to do is put in the middle the radius. And of course the radius is defined right here. We know what the radius is. So we can just put in a cosine 2 theta. This must be squared. Okay? So then we just have to integrate that. And of course, that would be 4 times the integral of 0 pi over 4 cosine squared d theta. Now, at first glance, this looks like a really difficult integral because what do we do with cosine squared? We don't have the derivative of cosine. If this is cosine squared sine, then we'd be no problem because we could just do a u substitution with a u squared du. But it's not that, so there is so we have to think about, go back to our trig days, and there is a set of formulas called the power reducing identities, a set of trig identities. So let's visit that for a moment. I'm going to erase that to get out of the way. So the power reduced, and they can be derived from the half angle formulas. If you remember the half angle formulas, you probably didn't see these power reducing formulas, but you did get the half angle formulas in your 142 class. So the identity says that cosine squared u is equal to 1 plus cosine 2u divided by 2. Or you could write that as 1/2 plus 1/2 cosine 2u. So this is an identity that's true in trigonometry, and again, if you'd like, if you want to, for me to work through it for you, I could show you how it's derived from the half angle formula. But either way, you want to kind of put this in your notes because this is something that's going to come up a lot when we're doing polar integration. Okay. So what that means now is I can rewrite this as 4 times the integral of 0 to pi over 4 of 1/2 plus 1/2 cosine. Now be careful here because this is 2u where that's u. So since this is 2 theta, that means in here I'm going to put 4 theta d theta. Okay? So now we have to integrate. Actually, I might just distribute that 4 through since we have numbers in there anyway. So that would be the integral of 2 plus 2 cosine 4 theta d theta. Of course, that d theta is times this whole thing, right? Okay, so now we're ready to integrate. So when you integrate this thing, of course, the integral of 2 is just going to be 2 theta. And the integral of 2 cosine of 4 theta would be 2 sine of 4 theta. But we have to take into account the fact that when we take the derivative of sine, it will give us cosine, but it's going to kick out an extra 4. So we have to divide this by 1/2. Because then 4 times 1/2 would give me the 2 that I want. Or not divide by 1/2, multiply by 1/2. And of course that's, I've got my limits here. So that's evaluated from 0 to pi over 4. And then we're going to evaluate that, so that would be 2 times pi over 4, which would be pi over 2, plus, now 1/2 times, 4 times pi over 4 would just be pi. Sine of pi is 0, so that just disappears. I plug a 0 in there, that's gone. Plug a 0 in here, sine of 0 is 0. So this ends up just being pi over 2. So that would be the total area of all that little blue space. Because remember, we took the area of the little half a petal, and then we multiplied that area by 6. That's why I end up with by 8. Because there's 1, 2, 3, 4, 5, 6, 7, 8 of those half petals. Okay, I think I'll stop the video there. I was going to do another example, but this video is getting kind of long, but I will do another video with this example where you find the area between 2 polar curves. All right?